Afternoon. Welcome back to our APRG seminar. It's my pleasure to introduce today's speaker, Debdip Ganguly from Indian Statistical Institute, Delhi. The title of his talk is L2 Stability of the Heisenberg Uncertainty Principle on the Hyperbolic Space. With this, I would like to invite Debdip to deliver his talk, and also I request all the participants to mute their microphone. Over to you, Debdip.
Thank you very much. First of all, I would like to thank the organizer for inviting me to deliver a talk here in this seminar series. So today I will going to speak on the L2 stability of the Heisenberg Uncertainty Principle on the hyperbolic space. So as the title suggests, most of the thing you have been familiar with that L2 stability. So of course, what I will describe what do you mean by the stability, and of course the Heisenberg Uncertainty Principle and on the hyperbolic space. So let's start with, so this is the plan of the talk. So this is the first I will overview what is the Heisenberg Pauli uncertainty principle. And then I will say that how the curvature plays an important role in the study. If you pose this problem on in a different geometry, then how this Heisenberg uncertainty principle and what is how it's related with the curve, what is the effect of curvature in the study of this Heisenberg Pauli uncertainty principle. And finally, the main topic which I'm going to tell is that the stability, what do you mean by the question of stability of any functional inequalities, and in particular the Heisenberg Pauli uncertainty principle. And so let's start with the overview. So first I'll start with a very standard or a very famous spectral inequality, which is sometimes called the classical Hardy type inequality on the Euclidean space, which states that for n greater than or equal to 3, the gradient of u square is greater than or equal to some Vx u square. Of course, this V is a non-negative potential Vx. It's a non-negative. So I should have said that this is a non-negative function. So this type of inequality is one can see that when Vx equal to a constant, that is gradient of u square greater than or equal to u square, it's not possible because the bottom of the spectrum in L2 Laplacian in our L2 spectrum, the bottom is 0. So we don't so depending on this Vx, we will say whether it's a spectral inequality or not or something. This inequality plays a central role in the theory of Schrödinger operator with singular potential. So we'll consider mostly the cases when Vx has some singularity. From a physical point of view, it describes the motion of a particle under the influence of a potential. So what is the related? What's the Schrödinger operator associated with this? Of course, in particular, it ensures this inequality. This inequality ensures the non-negativity of the spectrum of the associated Schrödinger operator. So what is the Schrödinger operator? L minus V minus Laplacian minus the potential. Of course, and if you take the L2 inner product, LU greater than or equal to 0 is equivalent to stating this inequality. So once we have this inequality, then we say that this Schrödinger operator has a non-negative spectrum. Okay. So depending on V, and we will see that most of the talk will be concentrated on the this potential Vx has some singularity. Okay. So one of the famous, of course, as I said, if Vx equal to 1, it's not possible in Rn in the whole space Rn. So the L2 spectrum of a Laplacian on Rn is bottom of the spectrum starts from 0. So what is the next? So let's see. So there's the simplest form of the Hardy inequality on the Euclidean space, where Vx I have taken to be some constant time 1 over x square. That is, there is this Vx is nothing but some constant divided by mod x square. Of course, that's why it has a singularity at x equal to 0. And of course, in the literature, this is a very famous Hardy inequality, and where of course where we have taken Vx to be Ch over. So the first question is, what is Ch? This is the best Hardy constant, and we'll see what is, and we know explicitly the Hardy constant. And another important fact that I have taken this n greater than or equal to 3, this dimension constant. So what happened for n equal to greater than or equal to 2? The situation is different in 2 dimension. Given any non-trivial potential Vx non-negative, no estimate of this form holds. No estimate for any non-negative such estimates holds. And this is due to the fact that Laplacian in 2 dimension is a critical operator. This is something to do with the Green's function of the Laplacian in dimension 2. You see that just the Green's function is a log Green's function in dimension 2. Once we go to n greater than or equal to 3, it's mod x to the some constant time. Up to a constant time, mod x to the power 2 minus n. So log x changes sign, right? But mod x to the power 2 minus it doesn't change sign. So something to do with this, that whether this sign changing Green's function play a very important role. So, have such inequality, such inequality does not hold in dimension 2. Okay, so from now onwards we will only consider the case n greater than equal to 3. So, and what is more we know about this Hardy inequality is this. So for n greater than equal to 3, the short form of the Hardy inequality is this gradient of u square, and this is the best Hardy constant, n minus 2 whole square u square by mod x square. And importantly, this constant is an optimal constant. You cannot, this is a sharp constant. You cannot have an inequality greater, with a constant greater than this. Okay. Now the obvious important question, another important question is whether do you have a equality case? That means whether you have an extremizer, right? So it can be shown that this inequality is never attained in each one of R. There is no extremizer for such inequality. Okay. So that's for the Hardy inequality. So we started with this potential, this constant CH, the best constant is n minus 2 over 2 over whole square and 1 mod x square. That's the Vx we were thinking. Now, how this inequality is related to the Heisenberg uncertainty principle. So let's start with some basics from physics. Why is this inequality interesting? So in quantum mechanics, the state is described by a function, the wave function psi, which the L2 norm of the wave function is 1. So psi2 can be interpreted as the probability density of the position of the particle. The psi square is represented as the probability density of the position of the particle. So immediately using the Planck channel, we have the in the Fourier space also the grade and the Fourier transform is equal to 1. So this interpretation of the probability, this psi hat p has the interpretation of the probability density of the momentum particle. So these are the probability density of the position particle, and this is the probability density of the momentum particle. Describe the quantum state. Okay. Okay. Now the energy of the system is this the potential energy plus some kinetic energy. So p square psi hat p square plus Vx with of course under the influence of the potential Vx psi square. If we use again the Planck channel, we have gradient of psi square plus Vx psi square. Now for dimension 3, so for the dimension 3, we know that n equal to 3, the best constant is 1 over 4. So if you take Vx to be minus 1 over 4 mod x square, this is nothing but, so then using the Hardy inequality, we can say this energy of this system is non-negative. Another interesting thing is that the Hardy inequality says that if psi is localized close to a point, that is where x equal to 0, if psi is localized, suppose the psi has the function psi has a mass most of the mass near the origin, then its moment has to be large, right? Gradient of psi square is greater than equal to 1 over 4 psi square. So psi square by mod x square. If psi is localized around x equal to 0, it immediately implies that gradient of psi square has to be at then the momentum has to be large. So this is somewhere this Hardy inequality is giving you some kind of Heisenberg uncertainty. So, but of course we will explicitly say what is an Heisenberg uncertainty principle. Okay. So in the literature, this Hardy's equality should be compared with a better known Heisenberg uncertainty principle. What is that? Gradient of psi square to the power half integral mod x square psi square to the power half greater than 3 by 2 grade psi square dx. This is a I will explain what do you mean by each of the terms. So in the literature, this inequality is called the Heisenberg uncertainty, Heisenberg Pauli uncertainty principle. Of course. So what is this says? If this inequality says that if gradient of psi square not too big, then psi square if psi square equal to 1, if you the wave function, so it's greater than equal to 3 by 2. If normalized it, then this inequality says this into this is greater than equal to 3 by 2. So this inequality says immediately that if gradient of psi square is not too big, then gradient integral x square psi square is not too small. So there is, if it is big, it's small. So there is a compensation. That is, because this product has to be greater than equal to 3 by 2. And this part is nothing but the momentum part, and this part is nothing but the kind of position part. Okay. So in other words, the function itself and its Fourier transform cannot be sharply localized at the same time. So what does it mean? So there is something in the language of Fourier analysis. This uncertainty principle states as follows: that if f is in L2 and integral of f square equal to 1, then the position uncertainty, this part is the position uncertainty, that is x minus a. So you are some localized at around the point x equal to a, then this is the in the Fourier space that has to be greater than equal to 1 over 4 pi. So again, what this says the function and its Fourier transform cannot be sharply localized at the same time. So this inequality actually says that, right? So this is the position uncertainty, this is the momentum uncertainty. This has to be at least 1 over 4 pi. So of course this I have taken this inequality from this. There is a nice article by Alladhi Sitaram in Resonance this in 1999. So what's the proof? So proof is very simple. So just integration by parts. The proof just integration by parts. So assuming, so let's so it's this works for any f in L2. Just for the timing, let's assume f has a compact subgroup, that it vanishes nicely outside the compact subgroup, or it has compact subgroup. So the integration by parts says that in a minus infinity to infinity, half f square is x fx f prime. So I am considering all other the boundary term is going to 0 because I am assuming f has a compact subgroup. Then use Cauchy Schwarz, that x f into f prime x, take the modulus, then use the Cauchy Schwarz. Then I got x square f, so f prime square, and then again I am using here to here I am using Plancher, and then less than equal to, so partial. So less than equal to x square f square half 4 pi square y square f x. Of course, without loss of generality, I can assume a and b to be 0, because you can use the translation for this, and you can multiply f with a phase angle, right? You can put 2 pi b, 2 pi I x b. So this is enough to prove this inequality for x equal to a and x equal to a equal to 0 and b equal to 0. And just using the Cauchy Schwarz, you can prove this, right? So, of course, if you are not assuming the compact support, then you have to work a bit. That you have to assume that because already given that f is in L2, then you have to show that f prime is also also in L2, and then you have to use some kind of absolute continuity of f to do this to say that there will be, because of the integration by part, there will be some boundary that will go to 0 if you do it carefully. So this proves the uncertainty principle just using the Fourier analysis. Okay, so that is what the function itself and its Fourier transform cannot be sharply localized at the same time. Okay, so this is just for in R. So this is the uncertainty principle in over R. Now the same thing what happens for n dimension, right? So you have to work a bit. So let's see how this uncertainty principle. So this principle, this excess, let's say a equal to 0 and b equal to 0. That is the integral x square fx square integral y square f at y square to the power half is greater than equal to 1 over 4 pi. How it is somehow it is like related to the Hardy inequality. Let's see how it is related to the Hardy inequality. Let's try to give a proof using a Hardy inequality. Okay. So you have taken 1, which is equal to, because I have normalized psi, right? Integration of psi square equal to 1. So integration of psi square, I have just multiplied by mod x and divide by mod x, and then just use the Helder inequality. That then, if I use the Helder, then will be psi square by mod x square whole to the power half x square psi square. This is, you see, this is the part we are getting. X square f square. Okay, x square psi square to the power half, and from here to here I have used only Hardy inequality, right? That gradient of psi square is greater than equal to 1 over 4 integral psi square by mod x. From passing from here to here, I have just used the Hardy bounded above. This term is bounded above by the gradient of psi square using the Hardy inequality. So you are exactly, we have got the uncertainty principle, but there is a catch. So if you see, when I stated this uncertainty principle, gradient of psi, so I have already, using this Hardy inequality, we have got this part. But instead of 3 by 2, I'm getting 1/2. So I'm getting 1/2. So just using Hardy inequality, we can prove this uncertainty principle, but we'll see that this 3/2 is actually the best possible constant. It's the best constant in the Heisenberg uncertainty principle. But here, if you prove using the Hardy inequality, we obtain a non-sharp Heisenberg uncertainty principle with a constant half instead of 3/2, because 3/2 because of the dimension 3. Okay. So there's the point that using, because here everywhere I have used the optimal Hardy constant and the Helder everything, right? But still we are getting, of course, we get a non-sharp version of a Heisenberg uncertainty principle. So using a Hardy inequality, you can obtain some kind of uncertainty principle, of course, which is not a sharp. So now with this, I can now state the final version of a Heisenberg uncertainty principle in the Rn. So the classical Heisenberg-Pauli well uncertainty principle states as follows: let for dimension n greater than equal to 3, gradient of u squared to the power half x squared greater than equal to n/2 integration integration u squared. Okay, and importantly, the constant n/2 is a sharp constant. Okay, of course, in this mathematical form, it was appeared appeared in this book by Well, and of course, this is due to the Pauli and Well. Of course, Heisenberg did not stated this uncertainty principle in this language. So later, Pauli and Well stated this in this form. Okay, so we have for any n greater than equal to 3, we have this. We have a Heisenberg-Pauli well uncertainty principle with a sharp constant. Sharpness is, of course, meaning in an usual sense. And the next question is, like the Hardy inequality, we said that there are no extremals, right? So here the question is, what are the extremals? Okay, so it was also very nicely studied. All the extremals means the sharp constant is given by this infimum. That is when the infimum is attained by some functions. Indeed, the extremals are attained by the family of Gaussian functions. Okay, it is e to the power minus lambda mod s square lambda. So all the extremals are attained by these Gaussian functions. So in the Euclidean space, the Heisenberg Pauli well uncertainty principle is very well studied. This we know the sharp constant, and we also know the extremals. The extremals are nothing but all the Gaussians of this form, e to the power minus lambda mod s. Okay, so this is completely what the overview of the Heisenberg well uncertainty principle in the Euclidean space. Okay, now I'll move to the second part of the talk. So how the curvature comes into play in the study of this inequalities. So let's, as we begin with as in the Euclidean case, we begin with the Hardy inequality. Here also we'll begin with the Hardy inequality. So a classical Hardy inequality for a Laplacian operator on the Riemannian manifold was due to Caron in 1997, which reads as follows: for n greater than equal to 3, the this is of course the gradient of G. This is the hyperbolic gradient. The Riemannian gradient u square dvg is this, and rho is the distance from x. Of course, but there is a catch. This Hardy inequality holds on any manifolds which satisfy the geometric condition, that is the Laplacian of the distance, so-called the distance function, should be greater than equal to c by rho. Okay. Now you can quickly check if your manifold is Rn, then is actually the Laplacian of R is nothing but n minus 1 over R. So your C is actually n minus 1, right? So in fact, what are the class of manifold for which it satisfies? So for example, it includes all the Cartan-Hadamard manifolds, right? Namely, a manifold which is complete, simply connected, and has everywhere non-positive sectional curvature. Okay. So for such manifolds, obviously this satisfies, and we have a Hardy inequality whenever this criteria satisfies by the distance function. Of course, we have to be careful with the cut locus and all those things, but generally speaking, that Laplacian of in all Cartan-Hadamard manifold, we have a Hardy inequality. Okay, so this was proved by Caron in 1997. So how now let's come to the Heisenberg Uncertainty Principle in manifolds. Okay. So it was not. It was by Cristalli in 2018 that MG be an n-dimensional Hadamard manifold. Of course, it's
Debdip, can you go back to the previous result? What was the sharp constant in case of Rn? N minus 2 by 2 square? Or?
n minus 1. C is n minus 1 for Rn.
So the thing is, this constant.
Laplacian of R is n minus 1.
This result is may not be sharp. This constant may not be. Does there exist some manifold for which n minus 2 by 2 square is
of course. There are some, of course, if you compute, there will be some Ricci term in general. So whenever you are working with some non-positive curvature, so you have such inequality. Okay. Yes. When you compute this row, it will become Ricci term, of course, plus some Ricci term. So automatically, if you have working on a Hadamard manifold, then you will have greater than or equal to this C.
Okay, I have one question. So if we assume the Hardy inequality, can we say something like this on the Laplacian, on the Laplace Beltrami operator? Like you're saying on this condition, the Hardy inequality holds. I'm saying, is there possible to have some sort of a converse?
There are something for such thing. Yes. Not exactly the converse, but there are something. Yes. But you can see immediately, if you're working on a sphere, you don't have such inequality, right? Because if you take u to be a constant function, because you CC infinity, right? One is a because sphere, if you take u to be a one, then automatically this does not satisfy, right? And you know that sphere is a manifold, is a positive condition, right?
Yes.
So you have to subtract something here, minus some. Yeah.
Okay.
So yeah. Okay. So now coming back to this HPW principle, this Heisenberg Uncertainty Principle. So the Cristalli in 2018 proved the sharp form of another interesting part. As in the Euclidean case, we have this is the best constant. This also remains the best constant for manifolds which satisfy this. Because if you see, because this best constant phenomena is coming because of this when your x is close to the singularity, right? So it's a local behavior. So the test function, the way you prove this is the best constant. This test function will have some kind of a local behavior. So it's not very counterintuitive that you have the same best constant as in the Euclidean space. That is another important point here. Right. So in this HPW principle also you have a gradient of u square. This is somehow a distance function u square greater than or equal to n over 2 integration of u square. Again, as in the Euclidean case, this n by 2 is the sharp constant, and x not being a fixed pole. That means where you have a exponential matrix and different. Of course, this inequality was of course not in the sharp form. It was also obtained by Earth in this PhD thesis in 2019. Okay, so now the Cristalli also reproved this with a sharp constant, but with a very important result. That is, he proved some kind of rigidity result. Cristalli proved that the following statements are equivalent. That is, n by 2 is achieved by a positive extremal for some x naught. Equivalently saying n by 2 is achieved by a positive extremal for all x naught. If this, then it implies if it is achieved by some positive extremal, then Mg has to be isometric to Rn. It has to be isometric to Rn. Okay. If this inequality is a positive extremal attained, then it has to be positive. It is not a non-zero extremal. Then the manifold has to be equal to, is isometric to Rn. Okay. So this he has proved this rigidity result. Okay. Now let's see. So what is one of the most important example of Hadamard manifold? It's the hyperbolic space. Let's see what happens in the hyperbolic space. Okay. So on the hyperbolic space, one could expect a final result for the Heisenberg Pauli uncertainty principle whenever the Riemannian manifold is model hyperbolic. What is an hyperbolic space? N-dimensional complete non-compact Riemannian manifold having constant sectional curvature equal to -1 or -c. Okay. That's the hyperbolic space. So Anderson and in 2003 and Combe in 13, they were expecting that Gaussians are the candidate for the extremal functions, right? But it cannot happen, right? By the previous rigidity result, this cannot be true. Moreover, these Gaussian means just e to the, instead of e to the power minus lambda mod x is the distance from 0 in Euclidean, you just replace that distance with the hyperbolic distance square, right? So that should be the analogous thing, that these hyperbolic Gaussians would be the extremals for HPW principle. But this cannot be true, because if it is for this inequality, if it is attained by if n by 2 is attained by positive extremal, then it has to be isometric to Rn, and we know it's not possible. The hyperbolic space cannot be isometric to Rn by the rigidity result. That means, of course, there are rigidity results in the hyperbolic space, but we will see that there is some curvature term present. Okay, you will see that in the, at least first of all, we see it in the hyperbolic space. Okay, so Cristalli in the same paper proved that let MG be an n-dimensional Catalan-Hadamard manifold such that the sectional curvature is bounded above C. Then for all x naught belongs to M and UCC infinity,
I have a question. So
yes.
The thing is, you are saying that Gaussian cannot be an extremizer because it's positive. But do we have a characterization of extremizer in this case, hyperbolic space?
Yes. I come to that. So that means this inequality has to be something different for the hyperbolic space if the Gaussians are the extremals, right? Because if the Gaussians are extremals, it can, suppose you just take M to be HM, okay? And you say that, okay, n by 2 is attained by the Gaussian, hyperbolic Gaussians. It's not possible, right? By this rigidity result. Not possible.
Are there,
right?
But are there, I am not asking about positiveness. What are there any other extremisms? Okay, you will come. Okay.
Yes, this is my next question. Indeed, these Gaussians are the extremals, not for this HPW principle, but with a sharper one. That is, so if this term is not there, this n-1 over n, some dc rho x1, I will come to that. What is this term? Suppose this is not there. This is if then it is greater than or equal to n over 2 integral m u squared dvg. That's our standard Heisenberg Uncertainty Principle. But you prove that in a Cartan-Hadamard manifold, if the sectional curvature is bounded above by a C, then you have some positive correction term. That is, this inequality obviously greater than or equal to n over 2, and prove that you can show that this term dc rho x naught, this term is at this -1, this is always greater than or equal to 0. That is, you have a better inequality whenever your curvature is strictly below 0. That is when the sectional curvature is bounded above by a C. Okay, and for this C is not, this is to do with the curvature. When C is going to 0, you can check immediately that this term is at this dc rho goes to 0 as whenever this C is going to 0. That is, when the sectional curvature is going to 0, that is the Euclidean case, this term vanishes. This term vanishes, and you have the original n over 2 integration m u squared dvg. That's Heisenberg Uncertainty Principle. So that means whenever you are in a Cartan-Hadamard manifold with a strictly negative curvature, you have an improvement of a Heisenberg Uncertainty Principle. Okay. And now you, in particular, if you take a constant sectional curvature of C-1, then these Gaussians are the extremals for plus this term, this corrected term of this extra curvature term. For this inequality, when C is -1, constant sectional curvature hyperbolic space, you have a Heisenberg Uncertainty Principle with a with a better uncertainty principle. What does it mean? Whenever curvature is negative, you have an improved Heisenberg Uncertainty Principle. That is the role of curvature in the study of Heisenberg Uncertainty Principle. Because you can see explicitly this curvature term arises in the inequality, this Heisenberg uncertainty, this Heisenberg inequality. And you can see that as C goes to 0, this goes to 0. That is, when you are Euclidean, this vanishes, you have a standard uncertainty. That means as the curvature is more negative, you have a better uncertainty, have a better inequality. Okay. And now coming back to the hyperbolic space, we have for such an inequality, you have a Gaussians at the extremes, positive extremes. Okay. So now we will now I will go to the second part of the third part of my talk. It's the stability. So now we have understood very nicely what is happening, how this geometry plays an important role in the study, and we have seen that we have a better uncertainty principle in the Heisenberg in the hyperbolic space with and we already also know the extremals are what are the extremals. This is the nothing but e to the power minus c rho. Of course, rho is the hyperbolic distance. Okay, so we proved, but it's not. We also proved that this identity, in fact, that we proved an exact identity for the Heisenberg Uncertainty Principle in the hyperbolic space, which says that this minus this is something lambda square this term. Now see, this term is actually what is earlier we have seen. Earlier we have seen that this minus this is greater than equal to 0. Now we have proved that this is nothing but equal to some remainder term. Now we want to have an equality. The equality case means this function u into e to the power rho square by 2 lambda square has to be a constant. Then we have an equality equal to 0, right? That is the equality case. And then immediately we can see that u is this some constant e to the power minus rho square by 2 lambda. That's the extremes, right? So this is another you can say that another proof of this uncertainty principle. But at least we have obtained. This is not anything serious result, but we obtained some kind of remainder term from which can directly say that what are the extremes. Okay, of course this is already known. Okay, now what do you mean by a stability? Okay, now the question of stability. So we define the set of all extremals in the hyperbolic HPW principle by c into e to the power minus alpha rho square x comma x. These are all the extremals, right? Now the question of stability is, does
so will
there
you
exist?
Sorry, Tristan. Will you go back to previous slide? Okay. Previous slide. Okay, so this lambda has to be okay. No, next slide. Sorry, next slide. No, not previous. You're moving backward, forward.
Oh, okay.
Sorry. Okay, that's
this one.
Next slide. Where you have mentioned this extremizer, there is a lambda. Okay, lambda is this thing. Okay.
I just now put 1 over lambda is alpha.
Okay.
Lambda is any alpha.
Okay, lambda is good. Okay.
These are the parameters for any lambda. Okay. These are all the extremals of Heisenberg. Now the question of stability. Does there exist a distance? Can we compute a distance where E is the set of all extremals? Okay, U from the set of all extremals is a suitable distance function from to U such that this is the, so if this term is not there, this square U comma E is not there, this is greater than equal to 0 is the Heisenberg uncertainty principle. Now I am asking a question. If this is, I term this as a Heisenberg deficit, what does it mean? This into this minus, you take the right hand side and minus greater than equal to 0. But now I'm asking a question. Instead of greater than equal to 0, can I prove this greater than with some up to a constant, some distance squared u from the distance u from E is the set of all extremes. Now look at it. How? If your deficit is small, when u is extremal, this is equal to 0, right? Then deficit is equal to 0. Now, but this gives a very important question. Suppose your Heisenberg deficit is very small. Then this, if we prove such inequality, what does it mean? Then u is close to the extremum, right? So your Heisenberg deficit is small. Then if such inequality holds true in certain distance, then your u is close to E. Right? What is it? E is close to the set of extremes. This is a very important question in functional inequalities. Of course, this is something related to PDE. So this is a question of stability. If your deficit is small, then whether U is close to the extremes. Of course, when U is in the set of extremal, the Heisenberg deficit is 0. Now, I digress a bit. The stability of various functional inequalities are very much interesting, and it's so recent time it has been studied in a very great detail. So it's starting from the L2 Sobolev inequality. It was for, I just digress a bit from the Heisenberg Uncertainty Principle. For any such question, you can always ask for any functional inequalities where you have a extremes, where we have a all classification of extremes. So this L2 Sobolev inequality, of course, we know for L2 Sobolev inequality, we have extremas and everything. So it was first proved, this type of stability question was proved by Bianchi in 91. And of course, by Figali, Maggi in 2018, Figali, Glaudo for a more general kind of equations for Sobolev equations, they have proved recently by Deng Wei-Chi, and it's like very important and very important contribution for the stability. Then comes the isoperimetric inequality. It's a famous work of Cianci, Fusco, Maggi, Cianci, Fusco, Maggi, Pratelli, Maggi, Figali, Maggi, Pratelli in 2010, and many. For Hardy-Littlewood by Sreyarian in 23, Chen, Lu Tang in 2023, and Hanley in so lot of function. This is the stability of various functional inequalities. And on Sobolev inequality on manifolds by Neumann, Spoilers, Rupert, Nobili, we also did something for L2 Sobolev inequality on the hyperbolic space and all this, the stability. So the question of stability is for all the question is the same. If you have an inequality, you have a best constant. The next question is, what if there are extremals? If there are extremals, then the question is, can you define some suitable distance such that the deficit is greater than or equal to up to a constant time distance from inputs? That is, whenever your deficit is small, whether U is close to the extremals. Okay. So let's now discuss what is this thing. So what is the state of art in the Euclidean space for the Heisenberg answer? So this slide is just digress from this Heisenberg Pauli uncertainty principle. This is just I stated some of the stability for various functions. Okay. Now again coming back to these hyperbolics, this Euclidean space, and what is the current state of art for this stability for the Euclidean space? So using the consonant compactness principle, McCarty and Venkataraman in 21 provided a positive answer in the Euclidean space that Heisenberg deficit is greater than constant time U square, distance square U from E of Rn, distance is this distance, infimum of this U minus, these are all the, you take the infimum over the integral U minus, these are the all extremals, this Heisenberg uncertainty extremals, U square dx. That's the standard L2 distance set from the external. So you prove that this deficit is some constant and this. Now, so Feti in 2018 provided a more constructive proof of the above estimate where these constant, this C1, C2 are explicitly computed. Okay, these are also very important to compute the stability constants, identifying the constants C1, C2 using Gaussian functional inequalities. And this is where they have used this more. This is a more PDE approach, but this is a more functional inequality, some Poincaré inequalities kind of approach. Finally, in 2024, obtained a short version of the estimate with optimal stability constant. They even they have also proved what is the best C1, C2, and everything. So optimal stability constant demonstrate that this constant can be achieved by some non-trivial function. Both this paper, one of the most fundamental thing used is the Poincaré inequality with Gaussian type measure plays an important role in the approach, in both this approach instead of the PDE. Why this Poincaré inequality comes into play? Let us go back to this inequality. If you see, if you just see, this black color terms are the Heisenberg deficit, right? This is equal to lambda square e to the power minus rho square by lambda square dVg. Now, if you just put u into E as V, that is gradient of v square, gradient of v whole square, e to the power e to the power minus rho square lambda by lambda square dvh. That is, if we can have some kind of Poincaré inequality with a Gaussian measure, then we could somehow able to compute. We will able to compute. We can go to this distance function, because this is exactly in the left hand side of a Poincaré inequality with a Gaussian measure. Of course, this has to hold for every lambda. Okay, then this should be greater than equal to integral u minus c u is whole square e to the power minus rho square dvg, and c, and then what is your u here? U is u into this. That is, then you can take out this and you can immediately, so you can say some kind of, you can compute some kind of distance. So this inequality actually gives you a hint that to prove some kind of stability, the Poincaré inequality with Gaussian measure will play a very important role. Okay, so let's see. So their approach is like that. But now the problem is, let's say same thing we can do in the hyperbolic space or in general manifold. But the point is, of course, we have some kind of Poincaré inequality with Gaussian measure. But here is the catch. This inequality should hold for any lambda, right? So there in Euclidean case, you can prove for lambda equal to 1, and you just use the scaling ux by lambda. You put scaling like u lambda of x of u of x by lambda, and then you will immediately get this lambda square outside, and your everything will be nice. But in general manifold, you don't have scaling, and you cannot do this trick, because you have to, this should hold for any lambda, because later on we have to use some, we have to put some lambda, some lambda, we can choose something. Okay, so that means we need to have now we are, the problem is now converted to another problem. What is that problem? Now we have to find some scale dependent, that scale means this scale lambda dependent Poincaré inequality with Gaussian measure in the manifolds. And yeah, of course, Poincaré inequality with Gaussian is a very well studied field. Of course, by the work of Bakery, Gentel, and Leto, there's a very nice book, this analysis and geometry of Markov diffusion operators. They have studied explicit all this thing happen, what happens in Euclidean space and this. So that if you want to see the proof, you just prove it for lambda equal to 1 and then scale it. Done. You have for any lambda such inequality. And once you have such inequality, this your u is nothing but u into e to the power something. So here you can immediately get some kind of distance function, u minus c. That's it. But now I have to study whether such things happens in the geometrical in a geometry. So more precisely, want to prove some weighted Poincaré inequalities of this form, that some lambda square, some function dvg greater than, of course, we want m lambda n lambda to be the Poincaré, the Gaussian measure. So of course, this, if you want to do this scale dependent Poincaré, this is something related. There's a very famous work of Millman, who proved that there is a deep result that triggers isoperimetric inequality, Poincaré inequality, and the exponential concentration of the ellipsis functions all are quantitatively equivalent to under a certain convexity assumptions. Okay, of course, again, Bakery, Gentil, and Ledo, and Villani also have some kind of very, this, of course, Villani gives a very nice curvature dimension condition to study Poincaré inequality to the manifolds. What is that? Now, problem is, now we want a kind of Poincaré inequality on the geometric spaces. Okay, so we tried that. We somehow proved that, of course, this is the Heisenberg uncertainty is greater than equal to some k times u minus c, exactly the L2 distance from these are all the extremas. So this is an L2 distance from the extremas, but we have some kind of weight. This we don't want, right? This we don't want. We want delta 1 should be k infimum, that's the distance function, but we have some kind of weight. And this is very bad. As this rho goes to the boundary of the hyperbolic space, this is going to be 0. So we obtain some kind of L2 stability, but with some kind of weight. This m is this is with a m. So this is not that good, but at least we get some kind of stability with a weight. Now we want to see that ideally this should be 1. this m should be 1. That's the ideal stability, that the delta, this deficit, should be greater than some constant time, the distance between the L2 distance from the extremes. So now our next goal is to prove whether we could get it like 1. M is 1. Can you get rid of this weight function? Okay. Now this is something coming back to this Villani and this work in Gentile, Gentile and Villani, which says that there is something called curvature dimension condition. So let Mg be a Riemann manifold with a measure mu having a density e to the power minus w such that the Ricci plus the Hessian of w, that's the weight function w. Of course, we want e to the power minus rho square by lambda square. W is, in our case, is rho square by lambda square. But this is a general theorem, says that if the Ricci plus Hessian is greater than or equal to rho by g, then we have a inequality. That the gradient of g u square e to the power minus lambda d mu is greater than rho infimum of this. Okay. But so in our case, what is our w? W is e to the power, you remember, e to the power minus rho square over lambda square, and lambda can vary from 0 to infinity, right? So we have e to the power minus rho square over lambda square. Now the goal is, let's try to, this is called the curvature dimension condition. So let us try to compute for our case w. Okay. So this is the curvature dimension condition. So minus n minus 1 gij plus whether we could get d square w by lambda square, because our w is rho square by lambda square. W is the hyperbolic distance function. So you have to compute the Hessian matrix. Of course, this is the Christoffel symbol. So if you compute the Hessian matrix of the rho square in the hyperbolic space, you will get that d to w is greater than or equal to 2 into gij. Okay, and 2 is the best constant we have computed. Now, so you plug this thing in this, we will get minus n minus 1 gij plus this is greater than n minus of n minus 1 gij plus 2 gij by lambda square greater than, we want that should be greater than or equal to some constant rho gij. But when, so finally we get this square by u square, this, so this should be greater than 2 by lambda square minus. Now if lambda is very large, if lambda goes to infinity, so you cannot get a positive a. It's not possible, right? If lambda goes to infinity. So this curvature dimension condition holds. This Villani's or Becquerel, those curvature dimension condition holds, but not for every lambda. For certain range of lambda, you could apply this inequality, right? But we want for any lambda between, for any scale between 0 to infinity, right? So this works for certain range of lambda. Okay. Now what happened after this range? Because we want to have such inequality for every possible lambda between 0 to infinity. Now you can use some kind of barrier arguments. So now we want some kind of lambda Poincaré inequality for alpha to infinity. 0 to alpha is guaranteed by curvature dimension inequality. Now we want something between alpha to beta. So alpha to infinity, alpha to infinity. So this case is divided into 2 parts. So we have done first for alpha to lambda using some kind of barrier type argument and carefully integrating the estimates. But another more difficult part is what happened for when lambda is very large. Okay. So there we have used some kind of we have modified our distance function somehow. So we have got some result. Of course, we get rid of this m to be 1, but the extremal have to, this distance function has to be modified a bit near infinity. Okay. So we got almost the result, but not, it's an almost, I would say, because it's not a very clean result like the Euclidean space. Okay. So that is what we have now. So thank you. So yeah.
Hello.
Yes.
Devdip, can you hear me?
Yeah.
Yes. Very nice talk, first of all. So I just have one question. So you said that you used some kind of barrier type argument. So I was wondering what kind of barrier did you use here? So
You
should
take
be
some
some.
kind. Yeah. You can take some kind of distance function and scale with log or something.
Okay,
Log
but like,
of
did you
yeah.
did you arrive like how did you find the barrier by analyzing some super solution sub solution or?
Yes, exactly. Just analyzing a supersolution. Yes.
Okay,
Yes.
okay.
You just take minus log of rho to the power some alpha and try to compute the Laplacian. So you will get, and then you have to carefully estimating some integral, and then you will get this. Somehow we'll get that C to be very nice, and he opted. But with this argument, we cannot get what is the best rho or something. You understand? So that is lost, completely lost. Yes.
Okay.
Yeah.
Okay. Are there any question from the audience? Okay. So I have a very simple question. The thing is, this you said that probably in the beginning I should have asked this. The gradient of u is greater than u square dx, whatever that constant will not be. You cannot take this v as to be constant, right? In that thing, the first thing,
Which one?
basic thing.
Here.
In the beginning. Yeah.
Okay.
So because of this spectrum of Laplacian, you explained something. How does that will come?
Which one? This one. Beginning. This one?
Yeah. No, yeah. This one. V, yeah. V, you cannot
So this,
take.
of
This
course,
is very
this is
simple.
trivially hold when Vx is 0, right?
Yes.
It's trivially
But,
hold when Vx is 0, very useful. So suppose you want some Vx to be 1, let's say. So it's not possible in Euclidean, right? Because the L2 spectrum is 0. The bottom of the L2 spectrum of Laplacian in Rn is 0, right?
Okay.
Right. So we say it has a Hardy type inequality if there is some Vx into use. So now look for the non-trivial V for which it holds, right?
Okay. Okay. Are there any other question from the audience?
Yes, I will have a silly question maybe. Can I go to that slide with involving that tan hyperbolic thing, the weight?
Sure.
So is it a locally integrable thing, this whole weight?
Locally integrable. Yeah, it's going to 0. It's going to 0.
Okay. But near infinity, this tan hyperbolic will behave like 1, right?
Tan hyper, when rho x goes to 1, and the 1 minus this is 0, right? 1 minus tan. So tan will be when rho x goes to infinity, this tan will be behaving like 1, right?
Yes. I see. You have a positive power. Okay, yeah. My question was, the question was like, instead of having this kind of weight, what happens when we try with general weights?
No.
General
Mackennap
kind of weights and things.
But we do not want to wait, right? We ideally want this.
No, I'm not related to this question. I'm saying in general, in this kind of inequalities, does it make sense to work with general weights?
Yeah. Something called Mackennap weight and all those things are there. Yes.
Okay, that is not very interesting, those things.
Somewhat, yeah. It's interesting, but I think that's been studied well, I think, if I'm not wrong.
So, and one more thing, like what happens when we replace this 2 by p?
Oh, so
even in the Euclidean case, what happens on that?
Yes, it's done in the Euclidean. Recently, it's been done.
And then in which question?
This same thing. This stability question with LP stability.
On the Euclidean space.
Yes.
Okay, so in that case, one cannot use this by integration by parts. But what kind of machinery one is planning to use in that? If I'm just asking, it's not a part of the class.
Of course. This uses this paper, Emmanuel Millman's paper.
Okay.
So they have
Okay.
a very beautiful Poincaré inequality with LP weights, and so they have characterized what are all the weights for which we have this kind of LP Poincaré inequality. They have characterized all that those things in the paper of Millman. So they use this work of Millman to give answers.
Okay. Okay. Thank you. Thank you, Bhair. Thank you.
Okay. So if there are no more questions, let us thank the speaker for a nice talk. Okay.
Thank you.
Thank you.
Thank you.